Welcome. Today we learn how to test claims with data. Think of it as a courtroom for these claims. The null is either guilty or not proven guilty. Judge probability wears a robe and carries a Z table. Hypothesis testing comes with a lot of new concepts and terminology and might sound confusing at first. But the idea is simple. Do we have enough evidence to convict the null hypothesis? Just like in a courtroom, big words will be used. Let's dive in. Hypothesis testing is a reality check for claims. We must first understand the claim and come up with a plan on how to gather data. Then we will summarize our data and prepare to state our case. If you take a large sample, say n equals 36, and find the sample mean to be 54 with a sample standard deviation of 12, would that be enough evidence in favor of this company's claim? We need to be careful here. We don't want to falsely get people's hopes up, especially if they are already clinically depressed. Null gets equality. Alternative does not get equality. The phrase more than 50% puts the boundary at 50, so the alternative claim becomes true mean is greater than 50. That's a right-tailed test. If our sample mean is 50% or less, we have no reason to even consider this claim. However, if our sample mean is higher than 50%, then we ask, is this difference statistically significant? That would be a test of hypothesis. Two mistakes. Type 1 is a false rejection of the null. Type 2 is a missed rightful rejection of the null. The significance level, alpha, is a number usually between 1 to 10% that you choose before seeing data. It puts a cap on type 1 error rate your test will allow in the long run over repeated sampling and testing. It measures your willingness to risk rejecting the null by mistake in search of the truth. So small alpha means you want to be very cautious about the null and not reject it unless you have very strong evidence against it. Large alpha means you are more willing to detect small differences as significant at the expense of a higher rate of type 1 error. An alpha of 0.20 is rarely appropriate. Treat those findings with a big grain of salt. Why don't we set alpha to less than 1%? The smaller the alpha, the bigger the beta, at least if everything else stays the same. A tiny alpha means we demand extremely strong evidence to reject the null. That makes us safer from falsely rejecting the null, but it also makes us more likely to miss real effects. In other words, lowering alpha protects us from type 1 errors, but it increases the chance of a type 2 error. It's like installing a very picky smoke detector. It almost never gives a false alarm, but it might also stay silent during a real fire. To calculate p-value, first you assume that the null is true. P-value measures how weird your data is under the assumption that null is true. The smaller the p-value, the weirder your observations. So if p-value is too small, we would seriously doubt the assumption that null is true. In other words, we reject the null. Decision words matter. We never accept the null hypothesis. In the court of statistics, we don't say innocent, we say not proven guilty by this evidence. So if p is below alpha, we reject the null. If not, we just say we don't have enough statistical evidence to reject the null. Courtroom vibes, but with fewer objections and more calculators. In practice, you only have one sample, but the test procedure is calibrated such that the rate of type 1 error doesn't exceed alpha over repeated sampling and decision-making for every value of the parameter under the null hypothesis. Hypothesis testing is reasonable decision-making in the face of uncertainty. Congratulations if you followed this presentation and understood everything. If that's not the case, no worries. Rewind and watch again. Be curious, not cynical. Assume the null, measure the surprise, and decide with clear wording. Science moves forward when we doubt nicely.